Hello. In my research, I have used a computational approach in order to achieve the optimum daylight inside buildings with using the automated kinetic shadier systems. As a first step, this is the workflow for my project and all of the steps that have been done during this project. In order to start in Grasshopper programming, I just created a parametric room whose all dimensions are changeable. So whenever you just define the number of x, y, and z, you can define the dimensions of room all parametrically. After I defined the dimensions of the room, I separated the source wall in order to define the windows on it. I wanted to define the ratio of window to wall. So I just considered a parameter in a vertical line, which was the height of the room. And then I defined a ratio based on which the top height of the window and the bottom part of the window could be defined. Next, I defined hours, months, and days in Diva for Rhino in order to have the sun vector for all hours of the year. So we can have from hour 0 to 1, 2, 3, 4, and so on of every single day of the year and every single month of the year. Based on the sun vector that I just gained, I defined a surface for the very first configuration of my shadier unit so that the normal vector of the shadier surface would be a bisector of between sun vectors and a target point inside the room. And this surface would act as a bisector of the sun vector and the target points in the room. Once I defined the configuration of the surface on which the unit was going to be located, I defined a circle with different radius on which you could define from a square to other polygons to even a circle in order to define the very first shadier unit. After that, all of other units on the surface of the shadier were defined based on this algorithm. So all of the units were defined one by one, each of which just getting the sunlight and then reflecting it to its target point. However, some important notes should be considered. The gap between each two kinetic shadier units should be so that the sun would neither directly could penetrate inside the room, nor it could be prevented from indirectly getting inside the room. So the distance between each two shadier units would be so that all of the sun would indirectly get into the room. Here you can see the logic based on which I defined the gap between each two surfaces. Then I arranged the units based on the bottom part of the window and the top part of the window, and this is a short video of it. Here you can see the final arrangement of my units with different patterns. And also here you can see how my units could have different patterns based on defining different segments for polygons. In this slide, I connected the B-reps into honeybee components in order to run daylight metrics simulation. In this case, I wanted to optimize the UDI, which was between 100 and 2000, which was the desirable UDI. Just a tricky thing. The period in which I wanted to optimize my UDI should be defined so that it would completely match with the moment in which my shadier was configured. By that I mean that, for example, here you can see that the months which is defined in diva and is defining my sun vector is month 1 and day 1 and hour 9. So I just defined an analysis period which started from month 1 from to month 1 and from day 1 to day 1 and from hour 9 to hour 10. Then I just connected this component to my occupancy files in order to just compute the UDI for only 1 hour. I used TT Toolbox to export my results to an Excel sheet. Then we started optimizing the model using Galapagos. And the model ran for 1 night, and here are the results of reinstated number sliders. Thanks for your attention.